Continuing our discussion on increasing throughput, now that you've identified the primary limiting factor, the primary bottleneck in your Kanban flow, let's focus on removing that bottleneck. So again, with the theory of constraints and the 5 focusing steps, we've already talked about identifying the bottleneck, how to do that. And then once you've removed it, finding the next bottleneck, now we're going to focus on removing that bottleneck. So number 2 here, exploit the bottleneck. Number 3, subordinate everything else to the bottleneck. And 4, elevate the bottleneck. Let's start with exploit. Again, exploiting is all about what we can do at the bottleneck stage itself. So the first thing we can do is reduce the work in process limit at that bottleneck stage. That's often the first step, reduce the WIP at that stage. The next thing would be to maybe change the process or the policy at that particular stage. Say the bottleneck is the review stage and cards are piling up at the review stage, for example, and it's taking way too long. The cycle time at that stage is far too long. So you might simply have to instate a policy change saying that as soon as something enters or is ready for a review, whoever is responsible for doing those reviews, whether it's an art director for art assets, or maybe a producer or a program manager or a product owner for maybe software features, as soon as something is ready for review, they should be notified that it's ready for review, and that review should happen as soon as possible. A third way to exploit at the bottleneck stage is if something has been stuck in a stage for too long, all the people who have the discipline at that stage should maybe drop everything else and swarm that particular card, that particular piece of value. Another way to exploit any particular stage is maybe add a buffer stage, meaning that as soon as something is done, right, instead of maybe tagging it as done, actually having a separate buffer stage as a ready for the next stage, or maybe putting a buffer in front of the actual block stage. So buffers are another nice way to not only see how long are things waiting as ready, but they're also a way to maybe exploit or help remove or reduce the bottleneck at the limiting factor stage. And the last way to remove the bottleneck via exploit is to use classes of service. Now we're going to talk about classes of service more specifically in the next module, but that basically boils down to how do we treat different types of work and how do we prioritize different types of work. Moving on to subordinate. So if we failed to remove the bottleneck at the stage itself, now we have to focus on the other stages in our Kanban flow and how could those be used to help remove the bottleneck. That could be as simple as maybe we have slack or we have a very high throughput in maybe an upstream phase or stage, or we have slack in a downstream stage. It could be as simple as taking resources or team members from those surrounding stages and having them focused on that bottleneck stage. Of course, that assumes that maybe you have T-shaped people, meaning you have people who can perform the various disciplines at all the different stages. Or it might mean moving people from a similar team to this team who have that particular discipline. The second thing you can do to subordinate, to remove that particular bottleneck, is to balance the flow. And that's something we're going to look at very specifically in our upcoming example. By balance the flow, that means we have to take a look at both our upstream, the things that happen before the bottleneck stage, and also the downstream, the things that happen after the bottleneck stage. So from an upstream perspective, we have to make sure that we're not, one, maybe starving the bottleneck stage, maybe not enough work is coming in there, which could be the case, or we might more typically be overwhelming the bottleneck stage, meaning that the previous stage before the bottleneck stage is producing or finishing cards much faster than the bottleneck stage can keep up. From a downstream perspective, you want to ensure that work that is finished at the bottleneck stage, it might be stuck in actually a waiting state. So there's lots of things being finished, but they're not being pulled into the next downstream phase because that phase might be the problem. When we talk about subordinating, we might be looking at maybe there's problems in the upstream stages, or there might be problems in the downstream stages. And what can we do to help remove the actual bottleneck itself? If we fail to exploit the specific bottleneck, what can we do there? Or through subordination, taking maybe resources from the other stages or balancing that flow. If we still fail to remove the bottleneck, then we may have to move to elevate, which means we have to invest in additional maybe staff in that specific discipline, or we might have to invest in additional training, or maybe invest in new tools or apps, essentially spending more capital to fix the problem. So let's go through an example of once we've identified a bottleneck in Favreau, how do we remove that bottleneck? And we're going to look at another game art asset team example. So we were able to clearly see, maybe just by looking at this particular column, that we're exceeding our WIP limit here on a consistent basis at this 3D model stage. More cards are piling up at this stage than can be completed in a timely manner. Or we might have used a CFD to analyze and find that this was the particular problem. Or to more accurately find the bottleneck stage, we may have used the calculation to determine which stage has the lowest throughput. And we're going to continue on from that perspective. By using that calculation to determine where we have the lowest throughput, we've determined that we have an unbalanced flow. So we're going to have to use subordination in order to fix this particular bottleneck at the 3D model stage for this game art asset Kanban team. So first of all, we've visually seen that cards are piling up here, but also using that throughput calculation, we've determined that this particular stage 3D model has the lowest throughput. To walk you through this, we can see that the three stages here, the three main actual work in progress stages, concept sketch, 3D model, and lighting. If we look at the average throughput per stage, we can see that this particular stage has a WIP limit of 5. And we've used maybe the control chart in Favreau to determine the average cycle time for this stage, which is 1 day. So we simply take that average WIP, 5, divided by the average cycle time, 1 day, and our throughput for this stage is 5 cards, or 5 art assets in this case, per day. Here at the 3D model stage, we have a WIP limit of 7, and we've determined that we have a cycle time of 3 days. So 7 divided by 3, we have a throughput, average throughput here of 2.33 assets per day. Here at the lighting stage, we have a WIP limit of 3, and we've used again the control chart to determine that we have an average cycle time of 1 card or art asset per day. 3 divided by 1 equals a throughput of 3 art assets per day we're able to produce at the lighting stage. So very clearly, we have a throughput of 5 per day here for concept sketch. We have a throughput of 3 art assets per day for lighting. But at the 3D modeling stage, we currently only have a throughput of 2.33 art assets per day. This is clearly our bottleneck. So what we've done is we've determined that we have an unbalanced flow. We have too high of a throughput here at the concept stage, which is overwhelming the 3D modeling stage, which is in turn starving the lighting stage. So what we need to do to fix this is simply balance the flow. So here where we had our highest throughput, 5 per day, we're simply going to subordinate the concept sketch stage, and we're going to take maybe 2 concept artists and swap those out. Maybe they're T-shaped. They can also do 3D modeling, or we could swap those out with another team. We're going to take 2 concept sketch artists, and we're going to remove those 2, and we're going to move them to the 3D modeling stage. We're going to go from a WIP limit of 5 at the concept sketch stage to a WIP limit of 3. And we're going to go from a WIP limit of 7 at the 3D modeling stage. We're going to add those 2 to a WIP limit of 9. And we're going to keep our lighting stage at 3. So what we've done by doing this is we've essentially balanced the flow. We can see that now here we've reduced the throughput at this particular stage to 3 per day. We've increased the throughput at the 3D modeling stage. We now have an average WIP of 9 at the 3D modeling stage. 9 divided by the cycle time, assuming that the cycle time at this stage remains the same, of 3. 9 divided by 3 equals a throughput of 3 art assets per day. And lighting we didn't change, so this will stay the same. The WIP limit of 3 divided by a cycle time of 1 art asset per day equals a throughput of 3 per day. We've now balanced this flow. Concept sketch is no longer overwhelming 3D modeling. 3D modeling is now no longer backing up. It can handle what's coming in from concept sketch. And lighting is no longer starved for work by the upstream stage 3D modeling. So by balancing this flow, we've removed the bottleneck at the 3D modeling stage. So how has removing this bottleneck improved this team's overall production capacity or production performance? You can simply ask yourself the question, how long to finish? How long to finish any particular batch size, in this case, art assets? And here we have another calculation, a little more math, but it simply breaks down like this. If you want to know how long it's going to take to finish any particular batch of cards, in this case, art assets, here's the formula. TB, which is time to produce a batch of cards, equals TC, which is time on board, or the lead time for one card, plus NA, number of cards in a batch, divided by 0B, which is output per day at the bottleneck stage. So let's use this formula to compare how long would it take to finish a batch of 50 art assets using our previous unbalanced flow where we had the bottleneck versus how long would it take to produce those same 50 cards with the balanced flow where we removed the bottleneck. So we'll plug in the numbers to this calculation. The time with the unbalanced flow to produce those 50 art assets, which is the time on board, the overall lead time for one card, which is 5. And that is simply taking the aggregate of all the cycle times at each stage. So the cycle time here is 1, plus 3 here, plus 1 here. For both our balanced and unbalanced, it's the same. 1 plus 3 equals 4, plus 1 equals 5. 5 is the lead time for one card, plus the 50, which is our batch size, minus 1, divided by our throughput or output per day at the bottleneck stage, which was in the unbalanced flow 2.33, equals 26 days. So it's going to take 26 days to produce that batch of 50 art assets. With the balanced flow, if we plug in the numbers, we have the lead time to produce one art asset is 5 days, plus that same batch size of 50 minus 1, divided by now 3 with the balanced flow, which is now the throughput of 3D modeling since we've removed that bottleneck, equals 21 days. By removing that bottleneck, by simply shifting 2 people from the concept stage to the 3D modeling stage, we have the same team size, but we've been able to reduce the time that it takes to produce 50 assets from 26 days to 21 days, a significant increase in productivity. And there you have it, a great example of how removing the primary constraint, the primary bottleneck, can lead to a very large increase in throughput.